Hello, hello. Let's start our random stream today. I guess I'm streaming every single day this week. Why not? Let me make it bigger. So plan for today is actually achieve what we strived to achieve 2 streams ago, and to measure actual motor parameters properly this time. I hope it will work, given that we solved the encoder issue yesterday and I cleaned the code a bit off stream, removing all the unnecessary parts. So let's do it. And let's actually start with inductance. It was the harder part 2 streams ago, actually 3 streams ago, when we were considering how to do it. And now that we already have the way to do it implemented, it should be very easy. We will just have to work a bit with our voltages and test if the code still works given our changes. So let's do it. I believe I actually don't remember as always where the code is for this test. So that is actually quite an interesting issue to have. Quite an interesting issue to have. Maybe in, this is bring up, right? Maybe in active experiments? Anyone? Does anyone remember? Yep, it is here, okay. Sure. Let's switch. Let's see, let's make sure we are on correct example. Let's make sure the software is correct. So we can measure all 3 phases, very nice. Set this. We don't use encoder here. Okay. Is set. Evaluate value. Evaluate inductance. It was good to me. Let's try and test it. Just first, let me lower the voltage to 12 volts first. Let's do the tests on 12 and on 24. So let's start with 12. And let's flash it. And also let's start with the AB phases. Okay. Experiments. It is. Okay. But first let's reset our debugger. Always quite an often issue. Okay, should be all right now. And let's run it, and let's see our values. Okay, it's very close to what we were measuring before. Actually, it is exactly the same, which is very nice to see. That's what we expect to see. Let's sure to note it here. Oh, actually, it is not exactly the same. Very interesting. It is roughly here. Okay. Noted. What do we do? Let's do all 3 phases first for 12 volts. And let's after that also do a 24 volts sweep. Oh, I know why it's happening, because we implemented a new feature. I see. Of course we did. Let's measure VC. Let's rerun. I think I will need to improve this example to measure all 3 phases at the same time, but not today. Or maybe today, if we will have time. if we will not have any issues as we always have, which is not likely, but possible. Okay. So the value is actually it's very close. It works much better with our improvements. The values are much closer. I'm actually very happy with this. And the last one. Let's see. Let's actually restart it manually, just to make sure. Okay, and again. What? What? The hell? Okay. I was confused because the value was getting smaller and smaller here every time I restart. Which is... what? But it's close enough to other values, so we might as well say that it is fine. So they're roughly close, they're roughly the same. Okay, and let's do the same examples just on the 24 volts. Let me increase voltage on my power supply, like that. And let's do it again. Let's do another sweep. We have time, right? Okay, I think I'll hit my current limit, so I need to redo this test with a better current limit. I improved it, so let's manually restart. Hello? Holy cow, it takes 3 amps. Oof. What? It becomes faster? Hello? No way, it shouldn't, actually. What? What the hell? I thought it would be the same, right? Very interesting. Actually, now that we're getting these results, we might as well go higher. Though, how much higher can we go, given that I have a limit on my power supply? But this is awkward, actually, very awkward. 15. Let's do all the phases first before getting any conclusions. Who knows what is happening? That's right. See? Okay, so the result does change. Maybe I was hitting the limit, the current limit in my previous test with 12 volts. Actually, I will need to retest 12 volts as well. Now thinking about it, we might as well do this as well. So let's note it. Close enough. Actually, it should be like this. Round it to this side. And here, 19. And let's do the first phase. Okay. Let's see what we get. Oh. Don't save. Measure. Okay, so all the values are very close to each other, which is to be expected, but they are different from other tests, which is unexpected. Okay, very interesting. Why is it happening? This is correct way to round it. Very interesting. And I hit, so let's calculate. 24 volts, we should hit roughly 4 amps, because we have around 6 ohms. So with my power supply, it can only provide 5 amps. We cannot get much higher. Maybe we can go to 30 volts, but this will be the limit. 30 volts is not that much to compare against, so we might as well not do it. Okay, now let's go back to 12 volts and retest with a higher current limit. Maybe 12 volts test was incorrect. So I'm back to 12 volts. I am saved here, and let's do the sweep again. Very interesting. Why is it happening? Okay. No, the values are the same as they were. Almost exactly the same. Like it's 56, and this value is 76, which is within the experiment error limit. Okay, I don't know why this is happening, but it is very nice that we found it. I will need to read up on this to understand what is going on, because I'm quite confused actually. I'm quite confused, as one would expect. So this value is almost exactly the same. And let's do the last phase. And let's see. Can I get more amperes from somewhere? Do I have anything to power the test? Okay, these values are very close to each other, which we expect, but they are not close to what we measured before, which is not what we expect. And this will be 51. Okay. And this test should be like 36, but we should expect a current of roughly 6 amperes, and my power supply doesn't provide 6 amperes. Though I do have 2 of them, but I'm not sure that I can connect them in series. I'm pretty much sure that I cannot do this, so let's do it like that, because we cannot measure it yet. And like this. As thing to measure, and let's assume that these values are correct. So we are working with 48 volts. And that means that if voltage increases and time constant decreases, that means that we should expect our 48 volts value to be even smaller, probably, most likely, possibly. But we don't know what the value is. We can only assume, and I will not do it like this. For now, I will just say that, let's say 13 is the value. So we can't do much better for now here. Can we? Can't we? I wonder. Actually, now that I'm thinking about it, did I even do it correctly? Maybe I should plot it. I actually think that I need to add to do. Add a plotting, debug plotting capability to this example to be able to manually check the results in case they are confusing. Okay, like that. So that means that inductance is measured. Let's quickly note it in our on-screen preview. We somewhat measured inductance, but we don't know why it is not constant. Okay, so next one is our torque constant, which will be a bit of a pain to measure. So let's start preparing. It will take a moment to measure. So And I will need to prepare the motor properly. Okay. We need to remove this cap. Oh, it's stuck. Okay. Unstuck. And where is my test cap? It's here. Is this the correct one? I don't think it is. Actually, I have two of them, and one of them is too long. So the correct one is shorter, and this one. So let's put it on. Very good, and let's also screw it. Screw it in place. Where is my correct Allen key? It's here. Is it? Yes. Okay, almost there, almost there. Good enough. And now we should have a functioning pressing motor, and we need to set up our table. Our table setup. Hello. So let's do it. Let's do it. We need to make sure that our motor is not moving anywhere. So clamp it to the table. Almost there, almost there. Okay. It is not that stable, a bit more. Still not that stable, not to my liking. Okay, still not that stable. Maybe I need to use two of them. That's better. Okay. Where are our kitchen scales? Oh. Here they are. And our test weights, just to make sure that we are calibrated. So let's turn it on. This is at 200 grams. Let's make sure that it is seen on stream. What is it? 200 grams weight. Okay. Good enough. Let's see, we will press roughly to the center, which is roughly here. And let's also make the measurement to see if everything is correct. Yes, we have exactly 10 centimeters here. Now we need to connect to our motor driver. That will take some logistics. Okay. So let's first turn off the power, remove the bugger, unplug our encoder from another motor, and unscrew the motor that is currently connected. Okay. And we will need to attach our second motor. I actually checked my stock today of my PCBs, and it turned out that I only have a single controller, like assembled one, for my last iteration, which is iteration 3. And I was rather shocked because I thought I had more of them. I actually thought I had like something like 3 and I only have 1. So I need to be careful with my controllers, with my single one, to not blow it up, or it will be very unfortunate. So let's connect our encoder. Okay. Holy cow. This cable is so short. Okay. Seems rigid enough to me. Let's make sure, because last time we had issues with encoder attachment quality. And let's connect our motor phases. Yellow comes here. Okay, they're a bit too sick, boys. A bit too sick. Let's unscrew a bit more. Okay. That looks good to me. I think this connector suffers a lot. I think I already broke the screwdriver attachment, so like a few dozen more screwing and unscrewing and the connector will be unfunctional, which is quite bad for a highly used prototype board. Okay, and let's connect the last one. Just like that. Let's make sure that all of them are rigid. That's rigid enough. That's as well, and this is also. Okay, perfect, perfect. Our cables are fine. This is connected, this is connected, this is rigid. So, and we are pressing roughly to the middle. Okay. So we can start. Let's actually set the camera. See the scale value. My mouse. And set up everything. So what we will have is bigger camera. We also need a table where we will put our values. One moment, I will open it up. So no, Google Sync Cube is not. Here it is. And we will also need our IDE, of course. And we will need it in debug mode as well. We need our start control in the current control mode. So comment this out and put current control mode in here, like that. So increase the scale here and move to KI and set another row. Let's say like that. Actually, we can copy this and follow the same pattern, just to be sure. And this will be like that. And let's center all of it as we can. And now, what do we do now? We flash our current controller, but we make sure that we are in positive direction. And we have a very small current task in the beginning, and we also need to make sure that our power supply says to 48 volts, which it doesn't. And now it does. So we are at 48 volts. How many volts do we expect? Hello, we expect 48, perfect. We are in current control mode, and what is our current control task? 300 milliamps is a bit too much. Let's say 100. 100 milliamps. This is an artifact of the past. I think it's looking good. Very nice. Let's make sure it builds first. It does. Okay, it will not flash because power is not on. I'm sorry. And we need to flash this one. Okay. Don't be bad. Okay, something will be broken now. I believe. Oh crap. 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 Everything is broken. Holy cow. Okay. I forgot to attach the debugger. Of course I did. Active experiment. Start control. Okay. Let's see. We are flashed. Perfect. Let's see our errors from encoder. We need to make sure that we don't have any, or at least as few as we can. And I added new structure for this. We don't need to see the code. We need to see only error values. Okay, and now let's start. And let me prepare to be hit in my hand. What? Okay, that was awkward. Okay. It does work, it seems, and it feels like it's very sluggish. 100 milliamps maybe it's too small of a task. For whatever reason, I believe it should be stronger, but it seems like motor cogging torque is too high. Okay, let me hold it. Let me reset our scales. Okay. Let's see, and let's also calibrate it. So browser, stay here. Let me take my calibration weight. Let's see if our scales are showing what we expect. 200 grams. Close enough. And now let's put our plunger here. Let's note the value. This value probably will not be correct, but it's close enough. 22.0. So let's start our work by increasing the values step by step. So second value is 200 milliamps. It is a bit stronger. Put it here, note the value, repeat. 76 grams. Okay. And again. 109 grams. Roughly 108.9. Let's see if they are close to what we measured before. They are close, but they are actually smaller than before. Very interesting. What? Why are they smaller though? Did I mess something in the controller? Very interesting, very interesting. Okay, let's keep going though. No time for pondering because motor getting hot. And we need to measure as much as we can, as fast as we can. So 0.4. Note and repeat. It is actually very nice to have a separate person to note the values when you do such experiments, but I don't have any available people around, so might as well do all of it myself. 0.5. Put it, note it, 189. Now we increase the step. So 0.75. Put it. Do we have any errors? We don't. But the motor is rather loud actually. Interesting how loud will it get when we get to proper currents. So what the value is 288.4. Let's see if it will break on higher currents. 1 amp. It's getting heavier. 387.7. Okay, it looks very nice, very linear. Next step is 125. Okay. Put it here. Note it real quick. 485.4. Again. Now let me actually show what I'm typing. 1.5. put it right number. 5, 4, 8, 4, 7. That actually gets quite heavy. 175. Put it here and write the number. 680 exactly. No, 0.9. 2 amps. 2 amps should be very nice current. 778. Good enough. Now we increase the step to 0.5. Okay. Put it lightly. Write down the number. And the number is 969. Noise. Switch number to 3. Okay. Put it lightly. 115. 4.7. 3.5. Is motor hot? And no, still not hot. But it will get hot very soon. 3.5. Put it lightly. Okay. 134. 0. 0.6. Okay, 4 amps. 4 amps. 4 amps. Oh, here. Oh, okay. Lightly. And write down the number. 151, 6.7. And it's getting really hard to get it off. 4.5. Okay. Put it lightly. Perfect. 1688.7. 5 amps. Okay. It's getting heavier and heavier. Oh, it was. Oh, crap. Okay. Oh, no. 1846.2. Can we go to 5.5? Motor is getting very warm. So if we do it fast. 5. Actually, let's do 6. Okay. Lightly. Oh, fuck. Okay, we definitely hit the limit. We hit the thermal limit, as you can see. Value is dropping, and value is dropping because the motor heats up, and when it heats up, resistance increases. And with increased resistance, current is dropping, and with dropping current, force is dropping. So I think we hit our thermal limit at 5, so we might as well stop, turn off the power supply. Motor is very hot. So 5 amps is effective limit we can measure. 4, which was very nice. And now let's see, and let's try to analyze our values. My setup is a bit of a mess, but it's fine. Not the first day here. Let me make my camera smaller and let's full screen our values. Actually, by 5 amps, we measured way more, which is nice. Let's see if we get an even nicer graph. I'd say this time we actually do not plot this value because this value seems to be off, like quite off. So I will use only these values. So let's insert our chart. And let's make sure that our C values are not here, but here. This looks very nice. Let's add trend line, and show our equation. Okay. Very good. So how do I make it bigger? How do I see more of it? Oh. Okay, so we still trailed downwards at higher currents, which is, I guess, fine. But this is linear enough. And it's actually better than this because here the trailing is much worse. So this is very good, and it also shows that with improved encoder firmware, we have higher torque constant. Hooray! So firmware improvement actually improved the force of the motor by roughly 3%, which is quite nice indeed. So let's do the calculations. Let's do our calculations, but this time we put here 375. And what we have is our torque constant is 0.367 and it was 356. Very nice, actually quite an improvement. And this value measured by this value, okay, which is correct. And we assume that we will only load a motor with 3 amps and oh, it's getting even hotter. Still on the 3 amps, we will never go higher than 3 amps. And it's actually will be nice to do. Maybe in the later streams, we will implement thermal control without a thermal sensor. So we will estimate how hot the motor is getting just by knowing what motor we are using, but not for now. For now, we also see that our stock value decreased as well. So this is our assumed static friction, though we are not sure if it is correct. But let's use it anyways. And what this value means is that we need 11 grams to move the shaft from 0. And let's assume that this value is usable. And let's calculate our friction torque, just an assumption, because we will need it for dynamic frequency measurement. So we might as well calculate it. So we multiply this value by 981 to get our newtons. And we also multiply by 0.1, which is the length of our crank, this value, so that we get the torque. And this will be what? Oh, and we divide by 1000 because we use grams and we need kilograms to use CI units. And this will give us Newton meters. Newton meters. Okay, looks actually quite reasonable. And that's that. We remeasured this value. It was much faster and we had, as I remember, no, I didn't look here, but I believe we didn't have any encoder errors. And also motor didn't become noisier with current increase, which is very nice, because the last time it was like a musical instrument, a rattler of sorts. So actually now thinking about it, shouldn't I subtract the weight of the plunger itself? Or shouldn't I? But this thing should be very light, right? Let's measure the one we have free. It's like 14 grams and at our crank length. Okay, most of the mass is here, so center mass is here, so the effective mass on the length will be roughly like 6 grams, 5 grams. But actually these 5 grams are quite a bit compared to this value. Okay, let's not do it. Let's assume that we done everything correctly, which we clearly didn't. Like this value is good enough as an approximation for modeling and for using in firmware. It's anyways much better than we had before. But yes, I do believe that the mass of the crank should be somehow included, though I'm not entirely sure how exactly. So let's note the value. Let's make another page. Sorry for the flashbang. Let's quickly fix it. No. Like that. Perfect. And let's add our, how will we call it? What is the correct way to name this section? It will be named conclusion. Conclusions. Or actually, no, conclusions. Conclusions is fine. It is fine. So let's add value. Okay. Let's also switch text to white. Value name, unit, value. And let's say like that. And also a measurement note. Note. Okay, and this should be a sick boy. All right, and this can be a small boy. Both of them can, and this should be a sick boy as well. Okay, so resistance. It will be a line to line resistance actually. Resistance. And the measure is ohms. And the value is 0.605, which we measured last time. Then let's also add a note. This note. Actually, okay, let's add all three of them. Why not? It will be AB. Same will be here, but BC. No, it will be no BC, correct? And this will be CA. CA. Here and here. Let's add our notes. Okay. Make it bold. Statement. Copy the values. Perfect, perfect, perfect. We can remove all the tables we don't need. Columns. It became bright again. And to save your eyes, I'll do it like this. Okay, put the line here. Now inductances. Sure, it will be line to line inductance. Inductance. Why did I use the big letter here? Not sure, but I think it should be bold. Resistance. Le resistance. A step at 24 volts. 24 volts, let's say it like this. And then let's increase the size of this column. And good enough. This is an awkward line, like that. Line to line inductance, AB dot step 24, like this and like that. It will be BC. This will be CA. Okay, millihenries is fine, and let's open up our notes in the code, because we were noting the values in the test itself, which is here. Okay, so one value is 1316, 1319, and 1311. Measured using M1, E2, I3, PCB, and the test example test function. Like that, and like this. 3 times, of course, 3 times. And this is done. This is a very nice documentation for anyone to understand what we were doing. Let's remove those. And how do I reset the? I do this. Okay, next we have our force constant, torque constant rather, torque constant. And this is Newton meters per amp. And the nodes must say measured using kitchen scales setup, add picture after the stream with the setup. Okay. Also, the current assumes IQ, which is our IQ current from our current controller. And the value we got is this number 03678. Actually 678. It's very easy to remember. 0367. Let's approximate the last digit like that. We don't need more than this. I would assume because our measurement error is much higher than this value, so we might use it like this anyways. Now, what we haven't measured yet are the back EMF constant, which actually we expect to be equal to this number. They should be the same in CI system. And in CI system, it is volts per radians per second. And also we need dynamic friction coefficient. And it will be, okay, what's the value? It will be Newton meters per radian per second, like this. We need to measure both of those. One is relatively easy to measure and one is relatively hard to measure. So let me do a short water break and we will measure this one first because it's easier to measure. This one will go first. Let me actually change the color here to not forget. Okay, looks nice, very nice. And a small pause. Be right back. Okay, I'm back. And to measure to other test, we need to actually remove this part. So let's do it first, because we need our shaft to spin with no limits. And where is my Allen key? It is here. That and remove this as well. Okay, we don't need the scales anymore. And we just need to see the shaft spin. So let's also update our description because we measured KI relatively decently. Acceptably, I'd say. Acceptable. So update it. And now let's see. Let's go to our examples. In the example code, we will need to switch to our speed control mode. Speed controller. Okay. So we are in speed controller mode. Actually, I haven't tested speed controller since we fixed the encoder. So I'm kind of scared to see if it works or not. Okay, let me check the values. Seems to be all right. And now let's actually add back the test code itself, which is here. And let's turn on our power supply. And let's flash our firmware. No, I don't need speed control mode. I need actually a current control mode. I'm a dumbass. Scheiße. Okay, current controller. Actually, and we will need to have. What exactly we need to have high enough current task, which we have here, like this, and let's refresh it again. Okay, let's run. First, motor will calibrate, of course. And then it should start spinning. Yes, with very high speed. Holy, I think it's actually became faster than before. Let's see if you have any errors. We don't have any errors, which is very nice. Very nice. So we are spinning like crazy, and let's see our values. We are spinning like crazy. So this value and this value, very nice. Actually, they are very nice. So let me put them to the separate page, which is here. Okay, this was our first investigation that came to conclusion that we have encoder problems. Now let's add another investigation. Of course, our volts and our amps. Oh, sure, we will also need to measure the voltage, which is fine, which is absolutely fine. So first we have our 48 volts expected. Expected. We will measure it. We have 0.11 amps of current, and our speed estimated is 91.39. Let me take my multimeter and measure the voltage on the lines without blowing anything up perfectly. But no promises here. No promises here. So let me do the voltage mode. cap it. Let's see. Here and here. What do we have? 47.6. Perfect. 47.6. All right, let's note it. 7.6 volts. Now we will need to flash an expectation of a different voltage, and also to limit the voltage in the firmware itself. So let's do it. Not in the firmware, but on the power supply. Here, let's move from 48 to 36. Let's flash it, and let me change the voltage on the power supply to 36. Very nice. Not sure if people enjoy this methodical work, but this is what people who work in the industry do. Who work in the industry do. And actually more than some people expect them to. Such tasks are relatively common. So we have 36 volts on our power supply, we have 36 volts as our expected voltage on our controller. And let's start it. First it will calibrate itself, and then we will see our values we need to add to our table. Okay, so we are spinning 68 point. Bus 68 only? The hell? 68.3. Maybe it does make sense, maybe it doesn't. Actually, it. No, it doesn't really make sense, does it? Yes, it's not really. Okay. Let me actually restart it manually and let's see if it will change. Not by a lot. Okay. Okay, so our current is 0.101. Right, proper rounding. Let's measure the voltage. Okay, without blowing things up perfectly. Minus and plus. And we have 35.80. Okay. Sounds good to me. So 35.8. Noted this, noted that. Let's move to 24 volts. Right here. Flash. And let me change the voltage of my power supply. Done. So let's run it. Calibration first, then we spin. And note the values. Okay, 45.27 with 0.0. Oh no, it actually does make sense. It looks so much better than it looked before. Oh my god, thanks god we fixed the encoder. Now it does make sense, and before it was such a mess. Actually, it looks very, very reasonable. Let's measure the voltage. Actually looks very reasonable. Here and here. And I see 23.84. 23.84. Let's do the last update, which is 12 volts. 12 volts. Let's flash, and let me change the voltage on my power supply. Done. And let's see. Run. Okay. Start spinning. Oh. No, this is actually... Oh, this is actually a very correct speed. It's looks so slow, and it's kind of slow, but it's very correct, as expected. Like, it's very much as expected. Okay, this is very good. And the current is smaller, so it's perfect. It's actually perfect. It's just literally perfect. Woohoo! Let's measure the voltage. Okay. And we have 11.89. Okay. Oh, we fixed so many things within Corafix. Holy cow, this looks so nice now. Okay, let's note it. 11.89. 9. Let me turn off the power supply, increase the voltage to 48 volts, change the 48 expectation for the next test. And let's analyze our values. Increase, remove, add, perfect. Let's plot some graphs. This is garbage, this is also garbage. I will keep it for history. For the history's sake. So let's analyze. What do we expect? This is what we expect, this is what we expect, and this is what we expect. So let's plot the graph of what over what. Current over voltage and also speed over voltage. We need two graphs. Insert chart, not like this. Remove, and this should be a line chart. And let's add. Okay, this is a very nice looking line, as we expect it to be. And this will be our, yes. Yes. Equation. Very good. Very good. Okay. We're getting somewhere. Definitely. So let's put it here for now. And also we need to plot our current over voltage. Actually, current over speed, I'd say. Current over speed. Insert. The plot should be a line. With this line being our... No, with this line being our main line and this line being our... Oh, what I've done. Remove and add this. Okay. Nice. And so now let's understand what these graphs show us. A small water break. Done. Okay. So this is our RPMs, and we need to also plot the graph here. Trend line, linear, label, equation. Very good. Very good. So our B is actually clearly seen on this graph. So what B says? B says is the torque that is induced when speed increases. And this is a line that represents current over speed. And our current is directly proportional to our torque in the motor. So the higher the current, the higher the torque. And given this we have a higher speed, the angle of this line is exactly our coefficient. So we just measured it directly, which is so nice. Let's see. So it will be quite literally 5, 6, 1, E minus 4. This is RB. We just measured it. This was so easy. Like it does make sense, correct? Right? Radians per second. No. It will be Newton meters per radian per second. So in our case, at 90 radians per second, we will get this value multiplied by this value, which is 50 milliamps, which is correct. Perfect. And we also have this value, which represents our friction current, and represents it's much better than we measured it at our torque measurement. So this value is 0.06 amps, and this is our torque inducing current. So we can actually compare. We need this value, which we have here as a number, and let's see if they are actually the same, if they are similar. So let's see, multiply this by that. Multiply this by that. This is our Newton meters. And what we got here. Okay, here we actually got less, so our actual friction is higher, or at least we assume it's higher. So it's roughly double this estimation. Very interesting. Okay. And this can be also part of the issue we were discussing when we didn't include the weight of our plunger into the measurements. Okay, so this is our friction estimation. Okay, so what does this graph show us? This graph should show us actually our back EMF coefficient directly, actually. Oh, sorry. I broke my headphones. 1 moment. Okay, plugged back. So what do we see here? We see our speed at voltage. So what we see here is 194 is measured in radians per second per volt. And what we want from this graph is volts per radians per second. So we would like this value divided by 1 divided by this value equals to 1 divided by this value. And let's change the format to text. No, format number. I would like to have more numbers, please. Custom, no, not currency, but custom number format, and I need 1 more 0. Right, looks good enough. And this is not even close. What the fuck? They should be the same. But actually, now that I remember, Calidro, here we were comparing what we were measuring. Where the hell am I? And here, this document says 0.53 Newton per amp as a current constant. And we measured almost close to this number as a back EMF constant, and back EMF constant should be equals to this constant in CI system. So maybe we somehow, somewhat, for some reason, have underestimation here. Maybe it's hardware, maybe it's software, maybe like there is no good reason. But this number does make sense as well. So it does make sense from what we measured, as long as our measurements are correct. So let's see, do they have back EMF constant? They do, but the measurement is volts per 1000 revolutions per minute. Let's convert this to volts per radians per second. And let's see if they compare. So how do we do this? Let's split our screen. And let's see. This is 30.9. And the measurement value is bloody volts per thousand revolutions per minute. Holy cow. I actually need to move it here because it doesn't even fit. And what we need to convert it to is we need to convert it to our volts per radian per second. So we have volts, so we need to multiply this number by thousands to remove the division by thousand. And our revolutions. Okay. This will be. Let's do it one step at a time. Let's do it one step at a time. This is volts per revolution per minute. And now I'm confused. Should I delete? No, not. Should I divide or multiply at this point? I'm confused. Okay, revolutions per minute. It will be radians. To get radians per minute, we need to divide probably by 2 pi. By 2 multiplied by pi. By the number. And we also need to divide by 60, I would imagine, to get seconds. Which is 1.9. Okay. And this number... What the hell? This number looks exactly like this number, but this is probably a coincidence. Right? What the fuck? What is going on? What is even this number? Like this number looks nothing as the number, like as that number, nor does it look like our number. Did I do it correctly? Multiplied by 1,000 revolutions per minute. Revolution is 2 radians. Do I need to divide by also pole per count? I think, yes, I also think that I need to divide by 4, which is our pole per count. And this makes much more sense. So we actually are close, very close. And why we need to divide by 4? Because this value only makes sense when it is applied to electrical angle, not to mechanical angle. Right? I think so. And if it does, if my assumption is correct, what we have here is actually a demonstration that they, in their datasheet, expect Ki to be equals to Ke, but somehow we got them differently. We got them separately. And what do we do about this? Like, do I assume that my current constant is incorrect? Do I need to multiply my current constant by anything? Actually, this is a very nice question. Do I even use a correct current? Okay, let me see. What if I multiply this constant? Because, hello Warsaw, what if I use this current and multiply it by square root of 2, sqrt of 2, and use a correct number of zeros, of course. How are we doing, Warsaw? Multiply by square root of 2. And put its correct number of zeros. And we get actually very close to the expected number. And why do I need to multiply by square root of 2? It's oh, fuck me. Let me think about it. Cool. Cool. It's cool that you are cool. I'm happy to hear it. How is the project on your side moving? Let me think. I don't want to trick myself into thinking that this is correct just because the number looks good. Because it may as well be taking desired for reality. What you missed? You actually missed quite a lot. I measured inductance, I measured the torque constant again, and now we are finishing measuring dynamic friction and back EMF constant. So I actually did as a whole motor parameter. I forgot the name. How is the stream called? Motor identification in like an hour. But now I try to figure out why the numbers don't look as I expect them to look. Because we measured our back EMI constant to be 1 divided by this, 1 divided by this, to be that. So it's 0.515, 0.515. We also measured this to be this number. You guessed that? It's nice that I added the plans for the streams on the screen, or you wouldn't have guessed that. And that makes sense. But what doesn't make sense is our current constant. And also I need to think here as well, because this radians per second speed is actually mechanical speed. It's mechanical radians per second, not electrical radians per second. Electrically, we will have here 4 times as much radians per second. So maybe our value is actually not close to the datasheet expectation. Right? Am I right or am I wrong? You didn't read that? Damn! My most reliable viewer doesn't read my notes on my screen. Now I'm sad. Okay, let me think. Does this make sense? The voltage does make sense. Do I need to convert voltage to something? It's 48 volts, but it will be actually less than that. It will be 24 volts because of conversion. So we need to divide by 2. Do we need to divide by 2 twice? My head hurts. My head actually hurts. So we need to divide our voltage by 2 because of how half bridges work. And I would imagine we need to divide by 2 as well because we use line-to-line values and we need to get our phase values. And if this is the case, then this value does make sense, right? Maybe? Okay. Okay, this value does make sense. Measured using M1 E2 I3 PCP and app user control with special example. This example will be moved. Update description when it does. So let's make it red as well. And copy here because they were measured together. On phone, keyboard block everything when typing. True. I get that. So now let's talk about torque constant. And what do we expect? We expect our torque. Like this torque coefficient is relative to IQ because IQ is assumed to be constant when we control the motor using FOC. Multiplying by square root of 2 makes sense only if we would like to get an expected sine voltage amplitude current, because the effective value RMS value is amplitude value divided by square root of 2. So maybe we actually measured exactly this value, because like they didn't mention like what current do I supposed to be using here. So I have no idea, like, did I measure it correctly? Did I not measure it correctly? What I know is that like what I measured is what I see, is what I can use in our firmware. And I would imagine that for me personally, this is the most important thing. Like the most important thing we can have. So should I leave it like this? I'm not sure I have enough brain cells to figure out anything new from this data. Or do I have enough brain cells? I don't think I have a knowledge. I don't think I have the knowledge to do it actually. Or do I? No, it's fine. I will leave it like this. Like, if I will learn something new, something that will give us results like better than what we have here, I will remeasure this. But for now, our measurement graphs looks awesome. They look exactly as what we expect. And that makes me happy. So I trust this number. I trust this to be correct for this number. I trust this to be correct for, let me actually put it here. KE, to be correct for what we are developing, for what we are putting inside. So we might as well, yes, this motor can run from 220. And maybe from this point, from this standpoint, maybe they were expecting in their numbers sine wave current, not a constant current. But I don't know, I'm not sure. Like, so the torque done, it doesn't matter. Your torque is proportional, directly proportional to your current, always. Like, there is absolutely nothing in the world that can change it unless you have a saturation in your magnets. Your torque is directly linearly proportional to your current, always, unless you hit a non-linearity limit. So you can measure it at 10 volts as well. You can measure it at 1 volt, but at 1 volt you will just have too much of a friction interfering with the measurement. And what is important is current, and current is proportional to resistance and voltage, and it doesn't matter at what voltage you achieve this current. So it doesn't matter that the motor is 220 volts. I can still measure it at 24 and get exactly the value I expect to have. And this value will stand even at 220 volts, if it makes sense. And this will be in volts per radian per second. So, and we also estimated a friction. So it will be static friction, and it will be Newton meters, and it will be 0.02, right? 22, like this. Okay. So I like these numbers quite a lot actually, and I can put as done for 2 more tasks for today. Actually, I did them way faster than I expected. I actually expected to run a separate test for back AMF. I forgot that the test for dynamic friction will actually give me our back EMF constant as well. Good to know that. So I guess at low voltage you have huge current. this motor does have switch current. If I were to short circuit it, it only has 6 ohms resistance. So if I were to put 48 volts at 6 ohms, I would get like 8 amps, and at 8 amps it will burn out in like 3 minutes, I guess. And at 220 volts, if you don't control it in any way, you will just blow up the motor in seconds. It will just poof, and the motor is gone. The motor is completely gone. And this was also done as part of this test. So this line is incorrect, and this line is correct. Do we have any other essential motor parameters we need to measure? Let me think. Let me remember the mathematical model. Friction, P, K, I. Resistance, inductance. I'd say this is it. So we actually measured everything in like an hour and a half. Hooray! That was way smoother than usual. Way smoother. What the hell is this? I remember. Remove. Remove. This is not needed because I do this here, and I need to rename it to KE and B. And here, I don't really think I need this page at all because I don't have any additional things to just measurements. Like we do need these pages because we have graphs here from data, but we didn't need that page because there were just direct measurements, and we have them here anyways. So let's make it a bit more beautiful. Like this, and like hello, like that. Like this, like that, and this should be from big letter, like this, like this. Actually, I'm so happy with these numbers. I can actually now take them and put them into my MATLAB model that I cannot show on stream for reasons, and update my parameters for my PID controllers and get even better results. And worse, actually, after fixing the encoder, the tests were very smooth. Like, we were only be able to measure all of it in half an hour and a half, only because the encoder works fine after our fixes. Without the encoder being fixed, it would have been a nightmare. But with encoder fix, it just was a smooth ride. So thank you for... Yes, absolutely no vibration, no noise as well. It was like very nice. Thank you for staying with me from yesterday and the day ago. Everyone who stayed with me, I appreciate the support a lot. And now we sowing what we... No, we're reaping what we saw. I think we will not need this today because I will use it off stream to calibrate controllers, and we will see the results next stream. No vibration, still 0 errors. Yes, exactly. 0 errors and no vibrations and no noise. And this is at 48 volts. So my war crimes with soldering iron yesterday were worth it. Okay, let's close it for now. We don't need this either, but we may as well need it later. So, stream is going way too fast. I only have one task, and I believe that this task should be relatively quick to implement. Let's first reassemble the motor so that we can run something while we are coding and make sure that our power supply is off. It is. Where is my screwdriver? Let's disconnect the encoder. Like that. And we don't need this connected to the table anymore. Also, Warsaw and everyone on stream, next stream, which is tomorrow, will be KiCad stream mostly. We will redesign the encoder PCB, but I think it will be very fast. But I also forgot how to use KiCad because last time I used it was a year ago, so I will need some time to readjust. And we will also test all the new KiCad features from KiCad 9 and 10, because like the last KiCad I used was KiCad 8. So in Core PCB update and KiCad feature testing will be tomorrow, and maybe some coding as well. We will see. So let's remove this. So follow if you want to see the stream tomorrow. I'm just saying. Okay. Let's remove this and that. Very nice, very nice. Let's attach back our main motor. Also, cool, I hope I will going early. It will be like a scheduled stream, so it will be 17 Central European time. Are you West Coast or East Coast? Like, how early is it for you? Like this. Okay. Feels good. And also attach the phases. Lost my screwdriver again. Here it is. Busy time, doesn't matter. Oh, really? Because I'd say it's still maybe too early, but if you say so, I'm happy to have you on the stream tomorrow. Anytime. So it's rigid. How do you spend your vacation other than eating cakes on weddings and designing your own version of a motor controller? And trolling me, of course. Like this. Check, check, check. Nice. Let's move it into the table because I need space for my keyboard, which is unexpected. I did not expect that we will be at this point so early in the stream. Let me remove my multimeter. Don't need it anymore today. One moment. This, like that. Okay. Okay, and let's run an example. Let's run our clock example, because why not? Actually implemented a fast start for this example. Position controller and clock example, and let's run it. Okay, it will not run because I forgot to enable my power supply. Okay, let's turn it on and let's enable flash. In FOC with braking, using 6 pins do STM32 required to deliver by hardware signal and its complement. Sorry, I don't think I got your question. in FOC with braking. Do you mean braking by brake resistor? And what do you mean by using 6 pins? Are you saying 6 pins to control the motor driver so that you provide dead times yourself? Requires the reverb by hardware signal and its complements. I'm not sure what yes. Can you please clarify a bit more? I didn't get the question fully. I'm sorry. No dead time done by driver. So there is a dead time register in timer, in control timers, which are timer 1 and timer 8, I believe. They can provide dead times, and you have to provide dead times, because if you will not provide dead times yourself, if you don't use hardware dead times, you will blow up your driver very quickly. And how to measure dead times, you better go and look up for some instruction files, because it's not a straightforward process. Or you might as well use a high number like 100 microseconds. Not microseconds, but nanoseconds, like 100 to 200. It will be safe always, but you will lose some precision on low and high currents. You do need to provide it, of course. And if you use brake resistor can be a separate channel. But it has safely of dead times, right? Yes, it does. So it can provide dead times itself, hardware-wise, and they are very good because they measure voltages. They are not time defined, time related. They are voltage related. So the drivers measure gate voltages and apply the dead times based on that, which is very nice because it guarantees that you don't waste any time on dead times you don't need. So the drivers is very good from this standpoint. So if you can use a hardware driver, just use it. And if you plan to use a hardware driver, why do you need 6 PWMs? Because 6 PWMs in this case don't make much sense. You might as well use 3 because like, why do you need 6? If your dead times are provided by hardware. Like the only reason to use 6 is to provide the times yourself. I believe. Maybe I'm wrong. But I hope I'm not. Okay. Let's run it. And our example should work. Hopefully. It does. Do we have any errors? Had a few, but not critical. Oh, we do have some errors. Interesting. Very interesting. Because in pure current mode, we don't have any. Oh, we do have them because our cable is longer. The length of the cable also matters, actually. Which I figure out, and I think it matters because my pull-up is not strong enough. I should probably use not 200 as I soldered yesterday, but something like 400. But I will not resolder it, given how much of a pain in the ass it was yesterday. So these errors don't break anything, and I'll allow it for now. Let's remove our code for measurement, and let's add to do here. To do. Move to a separate example test so that it can be run on demand on new motors. I have no ideas yet, but AI, as usual, confused me. It said it must use, for example, time 1 channel 1 and time 1 channel n and so on. Yes, you will need to use this if you want to provide a 6 PWMs. I personally work with 3, so let me show you. So here, I only provide high as PWM signals, which are all timer 1, channel 1, 2, and 3. And all low ends are just GPIO. Like any GPIO that I just pull to ground. And you can literally pull them to ground on your schematic design. Because like in the code, I quite literally, let me show you, pull them to ground and never touch them again. So let me show it. That I pull them to ground. Here, peripherals, GPIO. So this is my GPIO setup, and here I just put my C13, 14, and 15 low. I just reset them, and they stay low all the time. I just never use GPIO C anywhere in the code, like anymore. Like search, and only the setup function. And this is related to SPI, not to the driver. So I quite literally just do it here. And for enabling and disabling phases. Oh, actually, yes, you cannot pull them to ground. I'm a dumbass. You need to set them high to enable the phase. So yes, I do actually use them to enable phases like here. At least what those are used for. But this is just GPIO, just on or off. Nothing else. Nothing else. So actually you can just pull them to the power. Yes, I do use a 3 signal mode from DRV 8320. Yes, exactly. This is exactly what I use because there is no reason for me to use 6 mode. As I said, because driver provides good enough dead times. So there is no reason for me to provide the times myself. And now to our task, and our task is to implement safeguard for ADC setup. What have I done? What I've done. Dun, dun, dun. Okay. It just works. Let's go to our device definition file. And here, where is our ADC setup? It is here. And we will start working with this because I would like to provide additional safety measures for timing for our ADCs, because we are very close to pushing our ADCs over the limit. And we need to make sure that the timing calculation makes sense. So for that, what we will use is to actually see our ADC related registers and our ADC setup, which is here. And let's use a single example of a single ADC for now. So I need this, and these are all sequential. 0, 1, 2, 3, 4, 5, 6, 7. Perfect. So here, what I will actually do is to do a const u32. It will be u int 30. Oh my god, int 32t. IDC SMPR settings. Array, and it will be equals to. Hold on a second. Yes, what I need here is actually the durations themselves. So how do I actually measure 2.5? I know, I will just store 2, 6. We will only store the full number, the integer number from this number, and 5 we will assume as existent because we all know that it always exists, so we will just add 1 later in our calculation. So 12, 24, 47, 92, 247, and 640. So we can use these indexes to actually get the duration from this array. And why do we need this? So in breaking or run free, you need to manipulate all command pins. No, phases can stay enabled. You don't need to disable them because you control breaking by your PWMs as well. Unless, of course, oh no. Or actually, hold on a second. No, you will have a free run if you just enable all the PWMs to the single value. This will mean that high side transistors are always closed and low side transistors are always open. And this will be a free run. Right? Or does it actually mean that? No, it actually probably means that you have half time of transistors open and half time closed, and they all open and close at the same time. So actually it will be a free run. It will be just a free run where you have things both open to power supply and from power supply. And if you want an actual free run as it's supposed to be, you can just set it to 0 so that your low side transistors are always open. And in this case, you will get a proper free run without touching other pins. And for breaking, when you break using break resistor, it's completely independent. You just measure the voltage on your bus, and if the voltage is higher, you start opening the breaking resistor, breaking transistor, so that the power from the power supply and from your motor that is working as a generator can flow into the resistor to dissipate as heat. So this is a completely separate thing that doesn't depend on what exact motor driver you use, if it makes sense. And actually, I haven't implemented breaking yet, and we will do it probably the stream after the next stream, because the task we will do in a few streams will be gravity compensation. And gravity compensation we will implement just in a few streams. Let me draw to explain what we are going to do. So gravity compensation is when we have a motor. Oh, this is awful. A motor. And we have a crank of sorts. With some maths attached to it. And gravity compensation is when you can touch it with a force and it will move by itself as if the weight of this thing is equals to 0. And this is a way that industrial robotic arms work in special modes when they help you to manipulate high loads. So this will be a very nice experiment. We will only use a single motor, of course, because currently I only have one controller. Donate money for me to break more controllers. Joke. But yes, so we will add here like 200 grams, maybe 300 grams, because we know the torque constant here. So we know our limits, and depending on the length of this crank, we cannot load much more. And we will make sure that with software, we like actually feel 0 weight on this thing. Not 0 because we don't have like exact model of the motor, but it will be very close to 0. So this one of the examples we will implement soon. And for this to work, we actually need brake resistor to work, because when a load like this fails, or when I turn off the power, or when I just turn off the torque, it will fall and it will generate a lot of power while falling, because like of high moment of inertia. So there is high energy here, and this power will increase our voltage of the power supply and can break the circuit, or at least reset it. So we will need brake resistor so that we make sure that our voltage never exceeds, let's say, like 52 volts or something. Cool, I can't wait. That I need to know everything so that I can assign MCU pins accordingly. Sure. You are using my streams as a guide on how to make a motor driver, which is actually probably how it should be used, I guess. One moment. Water break. Actually, I ran out of water. Let me go fetch some water. Be right back. I'm back. So, another idea I have, and this is sorry, terribly sorry. Also, something we will work on very soon is I would like to use two motors and two motor controllers and to design a parallel SCADA robot. So that uses two motors. So we will design a robot like for 3D printing. We will work with kinematics, and we will use like our controllers and software on PC to synchronize two motors so that they work as a proper functioning SCADA robot. The counterbalance is what steering wheel use in electrical cars. What do you mean by counterbalance? I see. Yes, this is probably exactly the same thing to make the wheel feel lighter. Yes, this is gravity compensation, but in gravity compensation, you try to reduce the mass completely. And in what you describe, you just tries to reduce it slightly so that it's felt by the driver, but it is not too hard for driver to exhaust itself while driving. Yeah, something like this. We will implement in a few streams. Only here on this channel. So This is one of the things we will work on. Then we will have a parallel Scala robot, I would imagine. Also very soon-ish. I have quite a few ideas actually, but I'm not sure what order to pursue them in. And also I'm not sure how to think about the streaming thing. Like, is it a hobby? Is it something more than a hobby? Because no one follows me. So this will be a Scala robot, like XY, and we will move it from points, different points. Maybe we will put a pencil here. Pencil, oh my god. Pencil, and we will draw some fuck you Andrei or something. We will see, we will see. But here, now that we almost have a functioning motor driver, almost, we have a few things to add still. We can start thinking about like actual projects we can do with our custom motor driver. But first, let's keep improving our code. So we edit this. Very nice, very nice. Now let's use it. And we will use it in device definitions. So let's define ADC, current. What is the correct name for this? What is the correct name for this? What is that? Of sampling time. Sampling time, okay. Sampling time. And so put one of the. So I will switch to robot projects as excuse to not treat any FOCC crazy stuff. True enough. A very nice excuse. My streamer switched to implementing robots, so now I'm pivoting to robotics as well. Very true. So, okay. Okay, where the hell am I? Put one of the two. Oh my god, I'm so lost. To this value. Let's put it closer. To this from this enhancement and transcendent. I'm not sure if I typed it correctly. Enhancement enhancement. That H. Okay, and let's say we put this value here, 12. All right, so now we need to test if our we also need to set another one, define ADC MISC, which is miscellaneous sampling time, and we will expect the same value. So let's say what this will be 92. This exists, right? It does exist. Perfect. We put the same comment. And what does this give us? We also need to do define ADC current oversampling. And how do we define the oversampling? Like this. So we have options, and we need to add an array as well. but these options all look like a power of 2. So how can we approximate them with a formula? We can do 1 left shift by the config plus 1. This is a proper approximation. Okay, let's see it and let's test it, of course. Let's say we're sampling by 64, and let's say put one of this to, what was the maximum number? 256. Oh, from, okay, this is a bit unnecessary. From, yeah. All right. Do we need to check anything? We do need to check. Okay, let's to do it first. To do check if defined properly. The same, but for this, we need to do it for all of them, like that. What else? Do we need anything else? Oh, we do indeed need at least one more, but actually more than one more. ADC current oversampling shift. This value will be like that, 0 bit to 8 bit. Okay. Put one of the 2 8 bit from here. And let's put the value 5, and we will need all of it for automation of our calculations on how do we work with ADCs, because currently it is a pain in the butt to change them manually. So, how do we do this? We need to add a task for this as well. But first, is this board used for real project software implementation or for learning purpose? You mean my board? The answer is no. There is no project that currently runs this board, but I already did a few projects that needed this board before. They were small, like I was using my board for work. I was testing the ideas for the FOC controller we were developing at work on my PCB. So this project is mostly learning, but as I said, if it turns out that it works fine, that it works well, we will start working on projects. And currently, like you saw all the streams, we were struggling through a lot of issues, but we fixed all of them. Like all of them, everything we faced, we fixed. And now we are very close to actually start using this for projects. We just need to do a few improvements to the controller, which is we need to do full pull-ups for SPI, maybe inline registers as well. And that's actually about it. We don't need any other critical fixes, but I have some few small things that can be improved. And I just need to order the new version later, and this will get very useful. But this PCB is quite expensive. Like even a single one costs around $80-90. to manufacture. So I will probably order, and currently I don't have a client, so I don't have a lot of free money to spend around. But if I will have an option, maybe like in a few weeks, in a month, I will order like improved version, like a few of them, at least 3. I'd say like it will make sense to order 3 improved ones and see like what projects we can make. As I said, like gravity compensation is a nice project, but it's a project without a purpose. But Scara Robot is actually a very nice project because it can be used as a plotter, as a laser cutter, as whatever, and also as a huge experience, learning experience. So my current main purpose is to learn stuff, and if by learning stuff I will come to something, it will be nice. Why DRV offers all 6 pins commands? What's the advantage? Do we need that to charge batteries in braking mode? That's a good question. Like first of all, it provides this so that you are able to set your custom dead times. If there is an advantage, I'm not sure. Like I'm not sure how the recuperation works. Like I don't know how to charge batteries from the motor. Actually, this can be quite a nice project as well by itself. But I would imagine that it's a very easy, like now thinking about it, like if how I was to implement it, like my first thoughts would be to just switch our brake resistor for a battery and to push all our excess energy into the battery instead of our brake resistor. And this will be recuperation. So if this is the correct logic on how it's supposed to be working, then no, we don't need other 3 channels. But maybe the logic is incorrect, so we may need 3 other channels, but I'm not sure. In my head, currently it works without these 3 channels. The control of them by PWM. But I may not be fully correct. So, if... Okay, do we have it here? Let's see. Divided by... And if... And where are my timing definitions? They are in device. Interesting. Very interesting. They are in device. But I need them. Okay, let's move our ADC lower in this file. Because I will need to rely on some other definitions. Let's put it to the lowest possible position. Which is not here, but here. The robot will be using 2 stepper motors. No, the robot will be using 2 PMSM motors. Stepper motors are for losers, are for weak people. We are strong. We can do it on PMSM motors and custom firmware and custom drivers and custom everything. Who needs stepper motors? Well, I'm ready to suffer a lot. This decision will definitely make me suffer, but if you don't suffer, you don't learn, so this is the way. We will not use stepper motors. Okay, so this will give me 7, this number, and this number must be, let's say, minus 200, must be bigger than what? Oh, this will be quite a complicated preprocessor definition. Because I don't believe we can use variables in preprocess. Oh, can we actually? Maybe, oh, we can. Maybe we can. Let me see. Where is our array? Here it is. Let me first make it dirty, and then we will think how to make it proper. Define ADC current samples. Samples equals to this array of this setting. Okay. So define ADC current full samples will be equals to this value plus 1 plus, no, plus 13. 13? Yes, 13. Damn, so I'm also stuck with FOC movements and yes, you stuck with both FOC and robotics. Keep working, like, get to work. You are behind me, trailing behind me. Ay, ay, ay. No, you should catch up. Where is the PCB? Show me your progress. So this should be like this. And then we define. And then we. We use this value. We multiply it by this value by 1. Left shift by this value plus 1. Holy cow, this is complicated. And we add define ADC MISC samples, which is this value from that value, and it should be time for action from this value, and we add it here. Oh, and we put it in the parentheses. And here we set error. You suck. Okay. Let's test it. So it will break if I use here. It should break if I use here 37. It doesn't break. Fuck. Something is wrong. And what is wrong? What do you not like? Expression syntax error. Which exact error? Can you tell me? Do I have correct number of parentheses? This one more than should be more than full samples. Okay. Does it have CNC's enhancements? It is an H file and it doesn't have CNC's enhancements. Okay. Last time I saw Scara Robot doing plasma cutting. Yeah, and we will do something like this, but without a plasma because I cannot afford plasma, and without lasers because I cannot afford eye correction. But we definitely will do it with a pen and paper. Maybe lasers later, but it's like too long term for now. I'm sure we will be stuck at G-codes for a month, at least. System enhancements. Okay. And now it should work. Okay, it's an error. Oh, I'm a dumbass. Why the hell did I put this here? What? Okay. And this is incorrect. I cannot substitute an arrays in definitions in preprocessor. Now, I didn't know that. It do inverse cut editing. I saved it in my archive. What? What do you mean inverse cut editing? It seems like you are trying to sell some company secrets. Tell me more. Okay, so I suck because this is not possible. But what we can do is we actually can do it as a runtime thing. Okay, so let's actually keep all of this. We will do this because this is important, but we will move this check to a different place. So let's go to our device file then, and let's do a compile, not a compile, but a compiling definition. Compiled, rather. So let's say it will be error code, taking point of real material to duplicate the piece, achieve archive for YouTube. Taking point of real material to duplicate the piece. I'm still not getting it, I'm sorry. Words are confusing. You confuse me too much. So, do you have... I can paste link if you want. Sure, why not? Links are allowed in the chat. Include. Links are allowed, but I can still ban you manually. Okay. What do I want to add? The bucket seals are here. Oh, they are here, but they should have a definition of a type. Error. Okay, I see. So it will be if error code, and let's say device check ADC timings, and it should be a void function because all of them are defined. So let's go here, edit here, and what do we do here? We copy what we were trying to do here, but with this making much more sense this time. Okay. So let's say it will be you insert 2. My god. ADC current sample per samples. It's all right. Equals to this, and this should be fine. Yes, perfect. Then, and it should be a const value for optimization purposes. Const you insert t ADC current full samples will be equals to this. Just that plus 13. Okay. Where is my link? You promised me a link. Const misc samples in 32. Misc ADC misc samples equals to this. And let's say const u int 32t cycles per FOC period equals to this. this. And also, I think I have a better way to do it, given that we are in this file. And I would like to use current loop frequency, hertz, instead of... Where the hell am I? Instead of this value. This is much more correct. Looking for it. Okay, okay. Sure. Look harder. So what else? Now we need to do an error check, and the error check will be like what? It will be like, oh crap, like. We need to make sure if are okay. 1 second. Oh, this is like a 13 minutes video. Holy cow. I think I will watch it off stream, probably. But I see the gist. And what's about this video? Are you saying that you would like to make something like this, or something? So where were we? We were checking cycles per Foci clock. Cycles per Foci clock. Actually, let's go here and let's remove all of this. No, all of this. Okay. Go back to device. Minus 200. Because we need some space for error. And this should be just to see inverse card scanning what it meant. Okay, okay. If you don't mind, I will look after the stream because I'm not sure if other people are following our discussion. Because everyone else is silent. Okay. And this should be bigger than what? Then oof. 1 left shift by this value multiplied by what specifically? By this and plus this value plus 13. And let's actually the variable so that we can debug if it counts properly. Counts you in 32. You in 32. Timing estimation cycles goes to 0. 9. Oh, it can't be const because I have assigned to it. Okay. It cannot be const. So let's add all of this stuff here. I think I have too many parentheses. Yes. 1 too many. And here we will add this like that and return 1182 or whatever, and else we return 0. Okay, and let's run it in our main and let's see if our evaluation is correctly broken, which is supposed to be. So let's go to our main. And at this point, we can do it like at any points. Actually, let's do it here. And let's log our error. This function like that. Okay, let's try it. I have a member of my family last year wanted to buy a plasma table, so we did some research on YouTube pop this kind of SCADA robot, and here we are. I don't think that SCADA robots are good for plasma tables, if I'm being honest. I don't think it's a good idea. If you want a plasma table, do a proper CNC plasma table. SCADA robots are not for this purpose, like they're not that good. And you don't have any benefit from integrating SCADA robot into some linear system, linear guiding system. It's just more expensive for no benefit. Okay, so we were adding here, and now let's flash it and test it. Works. Okay, it doesn't work, of course, because why would it? And why would it work the first time? A no type name IO was yes. I know how to fix this. This is very easy to fix. We just need to remove this. We don't need it here. Still doesn't work because 37 doesn't exist. Only 47 exists. Okay. Sure. That's correct. And it still doesn't want to build, right? Multiple definitions. Let me actually rebuild the index. Okay. And build again. Nope. Multiple definitions of ADC and settings. Okay, so we have double includes somewhere. Can you show me it? Okay. Control main IO and timing utils IO. But that should be under the guard, no? What the hell? I'm in danger. And I'm rather confused. What do you mean? Where are my timing definitions? Where the hell are they actually? Cortex utils, okay. But I don't even use this in here, right? What the hell? But what have I changed even? If I remove this function, will it work? What? It still doesn't work. Like, what broke? What's broken? Like, what have I done? I did nothing. What is happening? Device definition. My camera broke. Okay, and it's fixed itself. Okay. This is not a redefinition, right? Oh, maybe I can't. Oh, maybe I know what's wrong. Maybe I know. I need. Oh, I know. I'm just a dumbass. Fuck me. Where the hell is it? I know what is wrong. Const. Static const. It will be fixed. Yep. I'm just idiot. Da 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 da. Da da da. You suck is correct in this case. Because I suck. Now let's try it. I know what the issue is. And how to solve it. Let's add this. This is incorrect. So I did mess up somewhere. Did I? This is 4. And 4 is here. Okay. 64 is 5. Where is the formula? Current samples. Current oversampling. And y1 shifted by... Oh, here I need +1. Of course. Right? Shift by 0. Or actually, I can just do it like this. This will work as well. This will work as well. Let's test it again. And let's run it. And the value is still wrong. Oh, of course it is wrong. Oh my fucking god. We also need to use the ADC sampling time. And this value we need to timing estimation. We need to multiply by... Hold on a second. I'm not sure the value I'd like to make even fits into integer variable. We have billions, but we already use millions. So we might as well get error due to precision. But if we divide first, we also lose values. Let's try and let's see later the results. So what we need to do is to actually use our this definition, and then we need to divide by the ADC frequency, which is definitely somewhere. Somewhere, not here. La 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 la. Hello. ADC. Where is it? Oh, it's just here. Okay. Okay. Makes sense. Makes sense. Multiply by this. I would imagine it only works nicely. Actually, on the other hand, there are definitely excessive zeros all the time. So we can safely do this. And this will guarantee the result within the inserted variables. Because we can safely do this always. If we are sure, and I'm sure. So this will always work. And now this timing estimation should be compared to this, and let's test it. And let's test it. And let's run, and we should get yes. And we get an error in our error log. What is my error? Hello? Where is my error? Oh. Like that. Okay, my bad. And now let's first test that we have error, and then we will test if we see the proper value when we set proper parameters. And we then need to update our ADC functions. And then it will work perfectly. Okay, and do we have an error in our error log? We do see that we suck. Okay, perfect. So now that we see that we suck, we can go either into the depression or do change our numbers, our values. Because depression is for the weak. Let's say 23. Is this a thing? No, 24 is a thing. 24. So, and let's test it. Now with 24, it should be a correct value. It should be within our boundaries that we set up. Let's see. Yep, we are very close. Oh, but we are kind of stuck. We still will have an error. Right? Yes, and this is because the way I got it, the condition. And this is rather aggressive. Holy cow. Holy cow. You know what? Let me go and change this. This is actually very nice that we see it. This function is too aggressive in the way it counts, but 100 is still breaking this. And for that to work, we need to change this to the next smallest, which is 47. Now it should be both a reasonable duration and no error. Okay, yep, perfect. And we should not see an error here. Yes, we don't see an error. Okay, so now we need to clean up quite a few things, quite a few places for this to work as expected, because currently it's a mock one. It doesn't actually affect how MCU performs. But we will do it after a short break. Be right back. I was out for 2 minutes and everyone left the stream. Fuck. Okay, alright. Sure. Go watch other streamers. So this is correct. Now let's implement it properly. Let's do all of those, but this is still questionable for now. We will need to edit later, but this will be useful as well. So let's do the checks. If this is smaller than that, oh, whoop. Actually, given that we are defining them as unsigned, they cannot be smaller, they can only be bigger than the biggest one. Which is that. Or we will probably need to do 2 errors per definition, because we need to make sure that it is defined like at all, and then that it is defined correctly. And if and I will always love you. Error must be between if and that. Hello. Warsa, do you think I suck as a streamer? I stream for 3 weeks and my viewership is hard stuck at 4 to 5. I'm hard stuck. Even def this and if then we do the same error. Same error. But it must be defined and must be. I don't think so. Twitch algorithm is not good. I hope so. I am planning to actually do a YouTube video. I have no idea how to do it. I suck at editing. I never done it in my life. But I plan to do a video, something like I designed a motor controller from scratch and it took everything and do like a meme description of my process of developing this project. Not a meme description, but a description with some jokes. A small YouTube video, because I think in technical YouTube it works well for people showing off their project even if they suck. And I don't think this project sucked at all. So maybe it will help. Or not, I think videos like this are highly depending on their quality, and given that I never edited a video in my life, it might be a disaster. On the other hand, any publicity is a good publicity, right? Oh no. Or no. So first is done, we need 2 more. 2 more and make sure that copy pasting errors are not here. This. But also this seemed to me like a device thing. But let's keep it here for now. MISC and here MISC and here MISC, and they have to be defined the same way, correct? And also here. Okay. that must be fine. The project is not beginner friendly, but it will teach you a lot of concepts at once. It's true, very true. It's completely not beginner friendly. And actually, I don't plan to do any beginner friendliness. Hello, I have a fly. I don't plan to do anything beginner friendly because like I will be bored by this. My beginner friendly days are gone like 7 years ago. I think I should learn something from what I'm doing as much as people can learn something. So otherwise it will be a waste of time for me, I'd say. So the values should be here and here. And also here. And here. So this is done, that is important. These two are implemented, but also let's move it lower. Here. Where they are not in the way. Yeah, 100% correct. Thank you. So my stream is for people with more than 2 brain cells, I guess. Rude, very rude streamer. And these are definition checks for ADC setup constants. Okay, so now let's use them in actual setup code. Oh, it's defined here. Very interesting. Okay, we will need to update this later. Precision question mark. And here, let's use, instead of this one, let's use what we've added, which is this. A crazy one like me, who's watching the clock. Oh, crap! I was writing so much code and it was showing a clock. Fuck. True. Clock was your idea of a project. You brought it on yourself. You would have been watching something different if you didn't suggest to implement clock. So it's your fault. I blame you. And everyone in the chat should blame you. A MISC setup here. And current or something here. Okay. Oopsie daisy. Oopsie daisy. MISC or something. And okay, I think I changed the wrong thing. No, I changed the correct thing. This one. So now it works. Now it affects actual performance. And this is very good. What do we need to do next? So this is implemented very nicely. Very, very nicely. Oh, it's so good. Now let's update those. And how do we update those? Actually, I was processing information and planning for pin assignment in my head. So the clock was a meditation for you then. I see, I see. ADC. Current. Precision, is it precision the right word? Bit count. Okay, it will be precision for now. I'm not sure if this is correct way to call it, but whatever. So how do we calculate it? Actually, how do we actually calculate it? The F32 version will be easy. It will be just float conversion of this. But this value should start from the default setting, which is 12 bits, and it should be somehow upgraded. Okay, we need this. We need this for sure. And this will be Oh, it's actually very easy. Hold on a second. It's 5, 0 by 5 bits. This will be a right shift. This will be a right shift by this value. And this will be a left shift by that value, but +1, right? Right. Okay, it is not as confusing as I thought it would be. It's actually rather simple, just lots of bit shifts. And let's say it will be test, so that we are not breaking anything for now. What are you going to do with the second SPI port? Not readable at all? What do you mean not readable? I mean not readable as a concept? Okay, let me actually explain. This PCB wasn't intended as a pure motor driver. It was intended as a part of the project. And the project was inverted pendulum, because like the project itself called inverted pendulum controller. So the idea was that inverted pendulum needs a motor to control the linear guide and also an encoder at the pendulum base itself. So that's why we have two SPI with the same pinout, so that we can attach two encoders, one for the motor and one for the inverted pendulum. But I'm not sure if inverted pendulum project will happen. Maybe it will happen, but later, because we have still quite a lot of things to improve before then. And also given our SPI issues, I'm not sure if we can have long cables on SPI. And without a long cable on SPI, we will struggle to design an inverted pendulum, because it needs to be like, we need to be able to communicate with like 2 meters cable for inverted pendulum to make sense. But currently we struggle with like 10 millimeters, 12 millimeters, 20 millimeters. Oh, not millimeters, but centimeters, 20 centimeters. So at 20 centimeters, we have like too much noise already. And maybe the next iteration with pull-ups will fix it. But for now, it's kinda not there to implement the inverted pendulum. Last line of code, define VDS. Last line of code where? What line? What file? Defines what? I'm confused. Let's see if those worked. Okay, let's flash. Your length define is not readable at all. What do you mean by that? What is not readable? Length define. What do you mean? What is not readable? Should I increase the size of something? Do I suck? Next week you will not understand it. Will not understand what? This? This line? Or something different? No, I will definitely understand this line. This line is actually very easy to understand. Like, it may look confusing, but I can explain it to you and it will be easy to understand. Let me test it first and then I will explain it, because this line is actually very easy. Like there are way more complicated things than this. Okay, it was compiled out because it is not used, but let's say test var int 32, another test var 1. And also let's do a float value. Float. This is not needed any longer. Should be 2. And here let's equal this to that line. Another test var 2 that line, but f32 test. Let's put them in our live view. Let's see. SPI for long transmission line, LVDS chip as suggestion. LVDS chip. Actually, this is quite a reasonable suggestion. I think I will note it for myself to actually read up on it because it does make sense. Actually, it does make a lot of sense. Let me note it for myself. Read on VDS diodes for SPI for long SPI transmission line. Noted. So let's run it, and it equals to correct value. It works. And now let me explain. When you will hear the explanation, you will understand that this is actually very easy. So the explanation of this line is that we have a default precision of the ADC, which is 12 bits, which is 1 shifted left 12 times, which is 4096. This is all it means. So it's just a default precision of the ADC. It's very easy to understand, and I can just make another definition to tell it. Then what we have, we do implement oversampling, and oversampling requires 2 parts. Oversampling requires the numbers of samples, the number of times you oversample, and then the number of times you shift this oversampling value to get your final value. And this is what's happening. When we say the number of times we oversample, we need to increase the resolution. So let's say if you oversample 2 times, you increase the resolution by multiplying by 2. If you oversample like 4 times, you increase the resolution by multiplying by 4. And multiplying by 2 is a left shift by 1. So if I say I increase by 4, I left shift by 1. If I increase by 4, I left shift by 2. If I increase by 8, I left shift by 3, and so forth. If I increase by 16, I left shift by 4, and so forth. And then when you say, and this is that part. So this is our resolution of our encoder after oversampling. But the second part of the oversampling is the reduction of bits, because you would like to clear out the noise. And the reduction of bits is defined here. And when we divide by something, we do a right shift. So let's say we were oversampling, like as here, 64 times. So we left shift by 6. And then we say we would like to right shift by 5 so that we reduce 5 bits of noise. And this is exactly what's happening here. So your default ADC precision, your oversampling, and then your oversampling reduction, like the thing that happens after you already accumulated all the samples. Yes, exactly. And this is done by the hardware. I don't do it in software. These all are hardware defines. I just need this number. I just need to know what I put into the formulas that use ADC. This is why I need those. And now that these are correct, I can remove this, remove those. And I don't need this comment anymore because it is now automatic, and these values should be calculated now. They should not be hard to find. They should be... Oh, actually, no. This is exactly this. Like, just like that. And now it's basic precision that we scale to the left and then we scale to the right after the samples are assembled. So this formula is not confusing at all if you know what you try to achieve. Like I can tell you this formula when I like woke up at 12 a.m. 12 p.m. Whatever the time is. I'm not sure. It's 2 in the morning. So now this makes all the sense in the world. And we also need to do the same error checking for this value like we do here. So let's copy one more time. Give me, baby, one more try. Like this, add here. And the values are from this. No, this is incorrect. And this is also not fixed. Okay. Okay, I see an error here. And I see an error here. Oh, I see so many errors actually. I actually see so many errors. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Correct. This is correct. And this should be here. And this should be here. And this should be this and that. And this and that. Copy pasting errors all over me. Okay, and this is a copy paste error, and also this is a wrong setup. This is the value we're supposed to have here. This is correct here. Now let's fix this comment and that comment. Okay. Hold on a second. Oh, I have even more errors. Okay. I need to do this and that. Okay. Does this look correct now? It does. This doesn't. Okay, and this does. Correct. Here. Current oversampling. This is correct now. Okay, and here. This is correct, and this is correct, and this is correct. Now it's working. Okay, perfect. AI teach me that yesterday, but still I didn't practice it. You mean ADC oversampling? ADC oversampling is not a hard concept to explain, but it's hard concept to use efficiently. Because it's technically a digital filter, and when we talk about digital filters, we are already at DSP junction of knowledge in the DSP territory, and DSP territory is quite a hard thing to learn. Okay, are we done with ADCs? So did we do all we were supposed to do here? Now I can control all of it. And half precision is not important. Does the code actually build? Thinking about it now. Do we even build? We don't. Okay, this is not important anymore. We already tested it. Anything else? Oh, it's actually built. Perfect. So we've done all our tasks for today. Hooray! What a nice stream. The first time we've done it. The first time we finished all what we planned to finish. And I'm not even tired. So should we continue? Do people want more action? If you do, follow. One follow and I continue. And no worse, a refollow doesn't count. Okay. Do I need anything else? Do I need anything else here? Let's see if any cleanup is due. This is new. This may be an issue. This may be an issue. This is fine. For now. Let's actually implement this then. No one followed, but whatever. Whatever. Don't follow, right?
Neg Vorsa just followed.
Yes! No, Vorsa! No! Why? Oh, damn, man. I was so happy and now I'm so sad that you were unfollowed and refollowed. You were an evil person. Fuck you. With love, of course, with love. With love. Okay, so let's actually do this. And how do we do that? We need to actually move the whole current control loop into an example. Because I quite literally don't want to keep it here. So let's do it then. We don't have much of a choice, after all. Let's just decide on a place where we store it. Vorsa is an evil person. So what options do we have on when to store it, where to store it? Bring up, is it the bring up part? It is kinda, no, bring up is a motor controller thing. And this is a motor thing. Should I actually create a small application for motor evaluation? Because it kinda makes sense. Kinda makes sense. So what test then there will be? We will test inductance, which is one test that needs to be done for 3 phases. And we also will need to test speeds for our dynamic friction and back EMF constant, which is also a few tests. But currently it's done kind of bad. Okay, let's do it in active experiments and then we will move it. Then we will move it into a proper position. So let's do it in active experiments. Okay. I'm still cannot get over how evil Vorsa is. What an evil person, an evil individual. So where are we? Let me move my screen and let's actually get back here with the camera. And this is a wrong letter in the wrong place. We are at active experiments. Here, let's add an experiment, which will be experiment 13. Example 13. And this will be measure B. Okay, Avega current and current speed main. Kinda makes sense, but it kinda doesn't make sense. IRQ. This will be time IRQ, time 1 IRQ, and we need another IRQ as well. DMA. Examples that are used for motor parameters. Identification. Specifically P and KE. Let's implement this. Example 12. What do you mean, Warsaw? Clock is confusing. I can switch an example from clock to something else. But clock is your idea, so suffer. Okay, let's switch it. Actually, Warsaw, let me see. Following things, April 19. You broke your following record. I know that you are following me from the second day I streamed. Oh, this actually produces errors. Quite a lot of them. Very interesting. Very interesting. It does produce errors. Okay, because we are using a long cable. Let's slow it down a bit. Let's slow it a bit down. Maybe it will be better. Let's see. Do we have errors? Right, errors. Hello? We do. We still do have a lot of errors. Whatever, it works. But it's very noisy. Let's actually... Pendulum effect. Now I float you at then and stream off my first view. Sorry? I didn't understand your point. Actually, I don't want to bother with this. I will just lower the voltage. Will it fix it? Oh, it's perfect. No errors. No errors whatsoever. Okay. What were we doing? Oh, we were actually cleaning up examples. Correct. Experiments. Let's add our launch sequences. Example number 13. Example 13. Main. Add this here. Just proper time RQ. And the same thing here. Average current speed. Main. And this will be DMA IRQ. Okay. This is not important for now. And now let's go and implement thing. So note like that. So we need to copy a lot of code. Copy a lot of code. Let's see. Let's call this. Let's go to this main. Okay, and let's start copy pasting. We do need this. We don't need that. We don't need that. we don't need this. This we do need. This we don't need. We also need this and that. Okay, all of this is getting copied. This example expects us to... Yes, so we do need this as well. Therefore, we need all of that and this. We quite literally copy everything. Just don't forget to close the brackets. A device encoder is unknown, which is fine. Let's define it. Somewhere here. Device encoder. Okay. Done. What else do we need? Motor FOC parameters. Sure. Let's define those as well. This looks correct. This needs an update from where exactly? From hello. Not here. Here. This value divided by 2. Okay, and we need FOC parameters, of course, which are here. Let's add them. Do we lack anything else? Motor inverter, but we do have inverter, we have test inverter, which should work just fine. Test inverter here, here, and here. Okay, one function is done. Let's do 2 other functions. How aggressive do we want to be here? I'd say it's fine. Also, I need to check my optimization level for this project. I'm not sure if it's set correctly. Let's do it really quick. Optimization, active experiments. Actually, it's done correctly, so perfect. Let's keep copy pasting our own code. We need this part and this part only, and this will be timer interrupt. We have all the functions for this, perfect. And now we need to copy only current loop related stuff from here. Oof, let's see. Oof, that's a lot of stuff. So let's start cutting. Let's start cutting away the pieces. Counter is unknown, but it's important. So let's add it to a global variable in the top of the file. Counter. Actually, I came to the conclusion that I need to rename it. It will be okay, with the counsel of me with myself, I decided to rename it to FOC counter. What? Okay, whatever. Whatever. Okay, that was a mistake. That was a mistake. Oh, fuck me. Why is it so hard? Okay. Sorry. Elevator music. um. Okay. Elevator music. I think it should be alright. Do we have a counter? Just a counter here? Like this? We have this and we don't need it. Anywhere else? We have it here. Anywhere else? Counter +1, of course. It would have been actually. Where are you? Defined. Okay, I see. I see why it is not breaking, because it is not active. Okay. I think everything is fixed. I hope. Is it used to use power 2 in... not sure what you mean, Warsaw. Is it possible to use power 2? What do you mean by power 2? What do you mean? Okay. This is broken. This is broken. If counter... but you will have a period that is not equals to your FOC period unless your FOC period is a power of 2. Like, why would you use it? Like, my FOC period is 20k. So if I use 1024, I will actually have 19 calls, and the next call will be shorter. Because at 19 I will have... What will I have at 19? This number. So the next call will be at 20,000 and it will not be correct, because we expect the calls to be equal in time. Unless you don't. So maybe you have a reason not to. Now for this to make sense, your FOC frequency should be like that. But this is actually a quite terrible value. It's hard to get with STM32 timers, I believe. I mean, adjust everything to be part of 2. But why? Like, I will not win anything by doing this. I will quite literally not achieve anything with this. Unless you have some specific proposal. I need errors. Error handling. Faster code is so expensive. It isn't. It actually isn't. The optimized reminder of division is 3 operations. You divide integer-like, you multiply integer-like, and you compare. So the actual implementation of a fast reminder of division for floats, not for floats, but for ints, it looks like this. You have your target value. And what you say is your first target value, and then you have your divisor. I'm not sure if this is correct spelling, but whatever. And then you have like int val, which is target divided by divisor. And then you do like if int val multiplied by divisor is equals to target. Oh, no. This is the wrong operation. What you do next is you just do your result of this operation is just your int to result equals to target minus int val multiplied by divisor. So this is your implementation. So you have 3 operations. One division, one subtraction, and one multiplication. And this gives you the result. And this is your optimized operation. So there is nothing long about it. It can be, and also it's not very long for floats as well, because like the logic is absolutely the same. You just need to also add rounding. Integer division is one operation, yes. Float division is not fast. Actually, is that's an interesting question. Cortex M4 int division number of cycles. Actually, 2 to 12. Maybe it's not super fast. 2 to 12. But okay. And what will the power of 2 give us? In this case, like, what is your algorithm to not divide? A reminder of division of power of 2 is 1 cycle. Is it? Oh, it is. It is. So to know that, we just simply do a bit mask. So let's say I know that you are talking from AI, but I know how to do it without AI. I know that reminder for 2 will be of this when we use powers of 2 is val, and let's say we need to, and let's say in this example we want to find by 64, and 64 is 2 in 6, so it will be value equals end will be value and not 0 0 3f. This is how it will work. And this is a one operation reminder of division when we use 2s. Know my experience with assembly with encryption. You have experience with assembly with encryption? Oh, you said you were working with RISC-V. Maybe you do. So yes, this will be a single operation comparison, but like to just save yourself 11 cycles, you will have to force all your prescalers, all your timings, everything, just absolutely everything to be a power of 2. I told you I'm everywhere and nowhere. Happens to the best of us, I guess. But yes, this is a good point. I didn't know this before. Like, it's when you tell it to me, it's very clear why, and it makes lots of sense. But no, I will not force my code to use everything as a power of 2, because for me it seems like a bit of a pointless optimization. Because I would like to have my code to be like reminder of division by 10. I just think it's nicer. Right? Or not? Now thinking about it, will it work if my frequency is not a power of 2? But if it is a multiple of 2, it will work. It actually will work. You know what, Warsaw? If I have 20k here, where am I? Where the hell am I? What? Fuck. In this example, if we say 20,000 here and we do it like that, it will still be 1 cycle. 1 cycle operation. Still will be. Not like this, but counter. So it still will be a 1 cycle operation. So the question is rather, for frequency, I remembered UART can save some errors if not respected. That sounds a bit confusing. Actually, that sounds not a bit confusing, that sounds very confusing. Can you elaborate more? Okay, so this does make sense then, and then I can actually, to do this properly, I can put here, let's say 16 and 32, and it will work absolutely beautifully and should not break anything, hopefully. Let's test it actually, UART control. And we also measure performance, but I didn't check the... Actually, let's do it. I'm curious. Let's measure the performance. Because we should see quite a bit of a difference, or should we? Like it's 16. No, I think it will be harder to see the difference. Can we check the disassembly? No, we also cannot because we have fast optimization which messes up the code. Okay, I trust it works, and I don't think there is an easy way to see if it works. But I trust it does, and I see no problem with having my frequency multipliers, divisors rather, as powers of 2. This is, I think, a good suggestion generally. Makes your code 20 cycles faster on every 16th and 32th iteration. Oh no, it actually does on every iteration because it's supposed to be run at every iteration. So yeah, it's actually 20 cycles improvement for every iteration. Now you are crazy like me, congratulations. I'm not sure if I should treat it as an insult or as a compliment, but thank you, I guess. What was I doing? I was implementing the example before we decided to talk about stuff. So let's get back to the example, and we have lots of things that are broken. Don't fix what not broken. So this is functional. What else? What else? Let's see. Finish raw angle request correct. Clean this correct. FOC counter here. Check errors. Calculate this correct. This is needed correct. This is not needed here. And where is an and if for this part? It's here. This is not needed here. This should change. This is not needed here. Let's define it here. Oh. Like that. a device position loop prescaler. Actually, why am I even doing this? We don't need this because we don't need position loop. Updating order position we do need, but position loop prescaler. Nope. Removed. Device speed loop prescaler. We need to update device speed because we need to measure it, but we don't need the loop itself. So removed. Device current loop. So let's see. Counter here. Electrical angle raw. What the hell is this? Why is it a global variable? I actually need to add it to some structure. To do add to some structure. And probably this as well. Right? No? Yes? No? Maybe. We will see. But now that this is not a part of a structure, let me do what? Let me copy this. Copy this here. Because this is needed, this is useful, this is actively used. So raw motor pole per count is also needed. It is also useful, used. What else? This is needed, this is needed. This is needed, this is needed. This is not needed. FOC, FOC. Oof. I don't have a current controller. Okay. Let's add it. Current controller. Let's add it here. So what else do we need for this example? We need a target. We need a target. A target. It will be equals to, let's say, 1000.0 milliamps. Hold on a second. Hold on a second. Include physics utils, and here we will do our favorite milliamps. So now that we have this, we need this and we need to remove that. We also need a flux controller, of course, and flux controller needs to be copied as well. Flux controller. Oui. Okay. Here we have. Oh, we also need a flux controller target, of course. Of course, and we need to do it as 0, and we also need to not forget to use F here. Okay, now I'm getting tired. So we will finish this task and we will end the stream. But this is still like 10 to 15 to 20 minutes coming. Hello, I edit you. What the hell? No, I did not edit. I am just a dumbass. Current flask target. No. Flux controller target. Flux, controller, target. Anything else? Test inverter. Okay. And run-up angle is what we need to add. Just a float variable. And it also needs to be renamed later. Because what the hell is this? We don't measure anything. Okay, and we need to uncomment this section. Uncomment it, and we need to add these variables. These guys. Where are you? Where are you now? Where the hell are they actually? Oh, here you are. Okay. Let's copy them. Okay. Quite a few unsorted guys. Here, here, and here. Should be everything we need. Should be everything we need. These comments are for the weak. We are not weak, we are strong. Okay. Let's test it if it works. Banned. You are banned, my friend. Okay. So now, will it work the first time? Will it work the first time? Let's see. Let's open main. Select proper example. Build it. Let's see what problems do we have. We don't have any, surprisingly. We surprisingly don't have any problems. And let's flash our active experiments. La 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 la. And let's see. Remove this, and that. The fuck is that? It definitely did not work. Do we have errors? We don't. Curious. These values suck as they are wrong. If I ever saw wrong values. Let's see, let's do it again. Fuck is this value? What? Current seems like it can be on the correct side. Maybe. And what is that? But the speed looks like it is not there at all. Actually, let's see what we measure as speed. Oh, I know, I'm such a stupid person. I'm just stupid. Fuck me. Fuck. Ay. Ay, ay, ay. Let's try again. And this motor, oh, I think it has more friction just because of the angle it's inclined. Let's see, let's run it. And let's see the values. I think I fixed it. Yep, fixed. Ha 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 ha. Oh. Okay, so this test works. We can clean up our main. Remove this garbage. It's not needed here any longer. And also add a to-do to document this implementation, how to use it, because I will definitely forget it later. To-do, document, to-do, document this function and how exactly to use this to evaluate B and KE. So let's see, do we have anything else we need to remove here? Maybe this can be separated into a function. Running inclined motor damaged its gearbox because of oil level. And what was the motor type? Are you talking about electric motor? And what was the power also? Tell me more. I think everything else looks fine for now. It's definitely not cleanest, but it's much better than it was before. Much better. 380 volts power motor. Holy cow. Holy cow, it should be very expensive, no? Like it's 3-phase motor? No, wait, you're from US, you don't have this 180 volts. Where the hell did you even run this motor? Like, what is the 3-phase voltage in US? It should be like 180 something. US 3-phase voltage. What? Ah, yes. 200 and... Okay, what the fuck does this mean? Oh, yes, this is correct. Oh, gearbox broken. Who cares about USA? True. What the fuck is a mile? Sorry. I didn't mean to be rude. Too much. I think we are done. We cleared this example. So we achieved one task more than we planned to. And I think I'm getting a bit tired. So thanks for watching. If anyone here is not following, please follow if you want to see more. Tomorrow will be a KiCad stream. Maybe some software developing as well. But mostly KiCad. See you there, I guess. It will be on scheduled, mostly, maybe a bit later. But mostly around this time. So thanks for watching again and see you next time.